So this is a part of my PhD thesis with my doctoral advisor, Joel Spencer. Some of you may have heard this talk before, but I really like this topic. And there are two parts to all my work with Spencer or with Ander Holroyd, with Tobias Johnson. The work that I've done so far, it combines two kind of unusual subjects or disciplines. One is mathematical logic, the other one is probability. And I have to say that I'm not a logician, and that this is really going to be a talk in probability. What we do, the role that mathematical logic plays in my work is that in some random setting, so it could be a random Erdős-Renai graph, or it could be rooted Galton-Watson trees that we are familiar with, I study properties that are defined by mathematical logic on these random structures and then try to analyze the probabilities of these properties. So that's the role that mathematical logic plays in my work. And for this talk, I'll focus on first-order language on rooted trees. Rooted locally finite trees, really, because I consider vertices to have finite degree. And we will consider that in the random setting of the Galton-Watson branching process that we are all very familiar with. Okay, so sort of the key parts of the talk, it's okay if you don't remember this, but I kind of wanted to give an outline. I start off with quickly recalling Galton-Watson branching process. Our results hold for very general offspring distributions, as long as they have exponential moments, so as long as they're not heavy-tailed. But for the purpose of this talk, I'll focus on the Poisson offspring distribution simply because it makes our computations a lot cleaner. And that's because of the Poisson thinning property that I will also talk about a little bit. Then I talk about the first-order language on rooted trees, define it formally, then give some examples. And then this third thing is perhaps the most important thing that doesn't make me a logician. It really boils down mathematical logic to combinatorial analysis. So I don't deal with formal mathematical logic anymore. The Ehrenfeucht games or the Ehrenfeucht-Frasse games, what they do is that they serve as a bridge between formal mathematical logical sentences or properties and their structural description on the random setting that we are considering. And the Ehrenfeucht games are my main tools for analysis. And finally, I'll talk about our results regarding the probabilities of the first-order sentences for rooted Galton-Watson trees. Okay, so Galton-Watson branching process we all know very well, but let's just quickly recall. So again, I'm considering offspring distribution Poisson lambda. So you start with a single vertex, the root, which I call R. And the root R will play a role. It's going to be it's not to be confused with the other vertices in the tree, as we shall see. That's the way I define first-order language. So this is why I keep saying rooted trees. This root is allowed to have Poisson lambda many offspring. So if it ends up getting any child at all, then you assign to each of those children mutually independently Poisson lambda many offspring again. And this you continue to get the random tree T sub lambda. So the reason why I use a lambda here is to denote its dependence on the mean lambda of the Poisson distribution. So as we know, when lambda is less than or equals 1, the tree will almost surely be finite. And when lambda is bigger than 1, there is a positive probability of it surviving. Let's talk a little bit about the Poisson thinning property. So what it basically says is that in a population, if you could categorize each individual into k classes, and the probability that an individual gets assigned to class I is p sub I, so that sum of the p sub i's gives you 1. And an individual gives birth to Poisson lambda many children, then the number of children in category I that the individual gives birth to is again Poisson, but with its mean thinned by the probability pi. So this is where the term thinning comes from. So each of these individual numbers are going to be Poisson lambda pi. And more importantly, they're going to be mutually independent. So this is what makes our computations a lot simpler when we are in the Poisson regime. So Spencer likes to generally give an example. So if the probability of a person being a boy or a girl is half-half, then the number of children that are boys would be Poisson lambda over 2. The number of children that are girls would be Poisson lambda over 2. And they would be mutually independent. So once again, what I described at the very beginning of the talk is this is basically talking about the role that mathematical logic plays in my work. So we borrow these various classes of properties that are defined by mathematical logic, and we study them on the random setting that we consider. So in this particular case, it's the rooted Galton-Watson tree. So, and the properties that I have studied so far are first-order properties, and in latter works, existential monadic second-order properties, but we will focus on just this one for the purpose of this talk. First-order properties are able to capture local structures inside the rooted tree, and we shall see why. Whereas these ones can capture much more global structures. Okay, so a formal view of the first-order properties, or what first-order language stands for in case of rooted trees. So the first-order language comprises finite sentences, and these finite sentences have the following components. So the root R, once again, is a special vertex. It's also called a constant symbol in the logical language. And then the other vertices are not to be confused with the root, and they're denoted by generally these lowercase letters. There are two relations that are very naturally arising in the tree setting. So the first one is the equality relation. So if I say that x equals y, it means that x and y are vertices in the tree, and they coincide. And the parent-child relationship, so if pi of y equals x, this means that x and y are vertices in the tree, and that x is the parent of y. You have the usual Boolean connectives that are also very common in mathematical logic. So this is disjunction or union. This is conjunction or intersection. This is negation and the implications. So finally, this is probably the most important thing that I want to talk about. You have quantifications, two kinds, existential and universal. And there is a reason why I have written this in italics. So in case of first-order language, you're allowed to quantify over vertices and not over subsets of vertices. So you cannot talk about there exists a subset of vertices such that something happens. This is allowed in the second-order language, and this is the reason why first-order language is confined to being able to express only local structures in the tree. So we shall see one example which is not first-order but second-order, and there I can explain through that example why first order is so different from second order. This is the main point of difference. So quantification only over vertices. Okay. There is a notion of quantifier depth which is involved with first order sentences. So what it is that if you take a first order property, the minimum number of nested quantifiers that are required to express the property is known as the quantifier depth of the property. Okay, so what do typical simplest first-order properties look like? Because it's important to understand what they look like in order to study their probabilities. So, and I have kind of summarized it in 2 bullet points, and I shall say why there are 2 separate bullet points. So, you could say that, if you could fix a finite tree, T0, any finite tree, and then you could talk about the property that there is a copy of this tree somewhere inside the original tree. So this is a first-order property. So you could say that there is a subtree inside the original tree which is isomorphic to T0. So as an example, if you consider the first-order sentence that there is a vertex with exactly one child, so is it more visible if I write there or here? I don't know, maybe there. It's in the dead center. So
exactly symmetrical.
yeah. So when I'm talking about this property, there exists a vertex with exactly one child. So I'm basically considering T0, which is this. This is our T0, and we are saying, okay, is there a copy of this tree somewhere inside the original tree? So this is a first-order property, and you can express it in this form. So there exists a vertex x, there exists a vertex y, such that x is the parent of y, and this part states that the only child of x is y. So for any other child z of x, z must equal y. So this is a first-order sentence, and hopefully that gives you an idea. And if you notice, you're talking about quantifications over vertices, but not subsets of vertices. Or you can say something like this, that you can fix a finite tree T0 of some depth d, and you can say that the radius d neighborhood of the root is isomorphic to T0. So the reason why these two are in separate bullet points is because the root is special. So what happens around the root is not to be confused with what happens maybe deep down inside the tree. So this structure could be present, somewhere a lot down in the tree, but what happens around the root it's kind of special. So, for example, if you say that the root has at least 2 children, then you can write it in this form. So there exists x1, there exists x2. Yeah, go ahead.
Say that x1 is not equal to x2?
Yes, you do. You're right. I should have stated that, and I probably wouldn't have fit it in here if I missed something. So yeah, you're right. I should have stated that x1 is not equal to x2, or negation of x1 equals x2. That should be the more formal way of saying it, and that both x1 and x2 share the root as their parent. Okay. So before I go into the general analysis of how we deal with, a general first-order property, which would look a lot more complicated than this one, I wanted to study an example to give you an idea how we started, dealing with this. So this first-order property says that there is a node somewhere inside the tree, could be far from the root, could be near the root, with exactly one child and exactly one grandchild. So the tree you're looking for is this. Okay? And the idea is that I want to be able to partition the space of all rooted trees into a finite number of classes, which in this case I say color classes because I'm denoting them by colors, as few as possible. In this case 3 works, but for more complicated first-order properties, you will need to classify into like several other classes. And we partition the space of rooted trees in the following manner. So there is green, there is yellow, there is red. When do I say that a tree gets classified into green? When it satisfies property A. So there is a node somewhere inside the tree that has exactly one child and exactly one grandchild. I classify it in yellow if it's of the following form. So this is green if A holds. It's yellow if the root has exactly one child, and then A does not hold, so negation of A holds. Okay, so this is the structure for yellow. And then everything else gets classified as red. So why do we do this? The reason is that after this classification, after setting down the rules for this classification, if you give me the root of a tree and then you give me the children of coming out of these roots, and you tell me the color classes to which the subtrees coming out of these children belong to, then I can tell you without any uncertainty what the color class of the entire tree is going to be like. So once again, if you give me the root, if you give me the children, and then you tell me the color classes of these smaller subtrees, then I can tell you the color class of this entire tree. That's the idea of this partition. And so how do I do that? So these are the rules by which I determine that. So if the root has at least one child whose subtree is green, then the entire tree is green because the property holds for one of these subtrees, so the property holds for the entire tree. So that's one rule. The second one says, this is a little, I want to draw this a little bit. So it says that the root has no child that has a subtree which is in color class green, no child with the subtree in color class red, and exactly one child that has a subtree in color class yellow. So you have the root here. This child is a single child, and this is in color class yellow. But notice that color class yellow means that this vertex has exactly one child, and then this is some subtree coming out of it for which A does not hold. But we don't care because now the root itself is the vertex which has exactly one child and exactly one grandchild. I hope it's visible from there. So once again, this entire tree goes into color class green. And finally, if you have no child with green subtree, no child with yellow subtree, and one child with red subtree, exactly one child, then you are in color class yellow. So once you have these rules, you can use Poisson thinning and these rules to find out the probability of a tree being assigned to color class green, which is X, and the probability of a tree being assigned to color class yellow, which is Y. And these are the equations. So if you can do this for any offspring distribution, but Poisson thinning just gives a lot less cluttered equations. And you can solve for this equation. So I denote the solution by f sub a of lambda because it depends, because of course the property A is mentioned here, and then lambda is because of the dependence on lambda. Two takeaway messages. We will make use of a general version of this analysis when we talk about general first order property. And the second takeaway message is that this solution is going to be unique, and it's a smooth function of lambda. So this is what it looks like. Well, 1 minus f sub a of lambda looks like this. So it's a smooth function, and you get it as a unique solution to those equations. In contrast, let's look at a not first order property. So the property of survival of the rooted Galton-Watson tree. This is an existential monadic second order property, and the reason is that when you try to express this property, you have to say that there is an infinite path. And the moment you want to say that there is an infinite path, you are talking about there exists a subset of vertices which becomes the infinite path. And this prevents it from being a first order property because the quantification is over subsets of vertices. So in this case, you can do a similar analysis and you will have two color classes, so two suffice. The first one is green, so for that the tree is infinite, and red when the tree is finite. And this is pretty easy to see that if the root has at least one child from which the subtree is infinite, then of course the entire tree is infinite. So you have green if the root has at least one green child, and red otherwise. So this is the classical equation for the probability of survival of the tree, again using Poisson thinning. And we know that the solution is not unique when lambda is bigger than 1, and that the solution is not differentiable at lambda equal to 1. So yeah, I just wanted to show this picture, but everybody's familiar with this. So the idea is not to say that second order properties will always give you something like this. It's to say that first order properties will always give you unique solutions to the first order properties. Their probabilities will come out as unique solutions to equations or unique fixed points, and that they are going to be smooth in lambda. And this is part of our results, which we shall discuss more towards the end. Okay, so now let's talk about Ehrenfreund games, because this is what's going to be our main tool in analyzing general first order properties, which are much more complicated. So the game is played on two given trees. So there is nothing random in this particular slide. You fix two trees, T1 and T2 with roots R1 and R2. Again, keep in mind the roots are special vertices. You're also given the number of rounds k, some positive integer, and it's being played between two players, spoiler and duplicator, who are very aptly named, actually by Spencer. So spoiler is trying to spoil the duplicator's life and prevent her from winning. That's his only aim in life. And duplicator is trying to mirror or duplicate the moves of the spoiler. Okay, the version that I describe here is only suitable for first order language. This game has several different versions depending on which logical language you're considering. So in each of these k rounds, there are two parts. So the first is a move by the spoiler, followed by a move by the duplicator. Okay? And so in each of these moves, what the spoiler does is that he selects one of the two trees, T1 and T2, and selects a vertex from the tree. The duplicator is then forced to select a vertex from the other tree. So the spoiler has a lot more freedom. He can go back and forth between two trees, but duplicator is stuck with the tree that the spoiler did not select. So, but what we know is that in each of the rounds, there will be a vertex selected from T1 and one from T2. By whom, we don't know. So xi is suppose selected from T1 and yi from T2 in round I. We also deliberately set the 0th round pairs to be the roots because the roots are special, so we want to keep that in mind. And here are the conditions for duplicator to win the game. So throughout the game, so for all ij between 0 and k, duplicator has to maintain the equality condition, which means that if xi and xj coincide, then yi and yj must coincide and vice versa. And also the parent-child relationship, which means that if xi is the parent of xj, then yi must be the parent of yj and vice versa. So you can tell that the more similar the trees are, where I say similar within quote unquote because it's not very, it's kind of a, I don't mean that the trees need to be exactly the same, although if the trees are isomorphic, duplicator will definitely win the game. But if they're similar in some sense, then duplicator has a higher chance of winning. Also, this is a full information game, so both the players play to the best of their abilities. There is no draw in the game. Okay, so what is the connection between Ehrenfreud games and mathematical logic? Let's say that we define a relation, I'm calling it curl sub k, which is on the space of rooted trees. So two trees are related by this relation if duplicator wins the k-round Ehrenfreud game on them. So the k is important, this parameter is important. Turns out that this relation partitions the space of rooted trees into equivalence classes, and let's say that sigma sub k is the set of all equivalence classes. It's really crucially, sigma sub k is finite. There is a really elegant proof of this, and if this were not finite, our results would simply not go through. The number of equivalence classes in sigma sub k is huge. It's a tower function of k, but it's very crucial that it's finite. So here's the theorem, which I believe is by Ehrenfreud, but I'm not sure, so I just wrote well known. So it says that if two trees belong to the same equivalence class in sigma sub k, then they satisfy the same first order properties of quantifier depth at most k. In other words, if T1 and T2 are two trees in the same equivalence class, and you gave me any first order property A, which has quantifier depth at most k, then either A holds for both of them, or negation of A holds for both of them. So it is kind of enough for us to look at the probabilities of the equivalence classes in sigma sub k. So that's what we focus on from now onward. So suppose P sub lambda is the measure, the Galton-Watson measure under Poisson lambda offspring distribution. So we are interested in finding P sub lambda of A for any given first order property A of quantifier depth k. So what we do is we just find out which equivalence classes in sigma sub k satisfy property A. In other words, sigma sub k of A is the subset of sigma sub k, such that if you were to select any small sigma from sigma sub k and pick any tree from that small sigma, A will be satisfied for the tree. Which tree you are picking does not matter from the previous theorem. So then P sub lambda of A is simply the sum over P sub lambda of these small sigmas that come from this subset. And so all we need to do is analyze P sub lambda of sigma for all sigma and sigma sub k. Okay, so as I said, that first example was there for a reason. We are going to try and emulate the argument that we had there. So the argument that we had there was with color classes, 3 color classes. In this particular case, we are going to repeat that same thing with the equivalence classes we just defined. And what we need to do is, given the root, so here's the root, and it has some children, and those children have subtrees coming out of them. If you tell me what equivalence classes these subtrees belong to, then I have full information as to what equivalence class this entire tree belongs to. So that's the same idea getting repeated. So let's say that n sub sigma is the number of children whose subtrees are in this small sigma, the equivalence class small sigma. Then all we have to do is look at this vector. Okay, so you might ask, why are we looking at minimum of n sub sigma and k? And instead of looking at each particular n sub sigma value. And the reason is that a k-move Ehrenfreud game will not be able to differentiate between n sub sigma, which is k plus 10, and n sub sigma, which is k plus 20. It doesn't distinguish between them. So yeah, go ahead.
T of ui, I got a little lost.
Oh, these are the trees that are coming out of these vertices, that's all. So this is a subtree which is coming out of ui, and it could be infinite. That's why I kind of drew dotted lines here. We don't care, as long as we know what equivalence class they belong to in sigma sub k.
Thanks.
Yeah. So this is the vector that will completely determine for us what the equivalence class is for this entire tree. And this truncation by k, which is almost acting like a cutoff, is what's making the number of equivalence classes finite. If you had to look at all individual values, it would not be finite. Okay, so So here's the idea. Instead of like going through the text, let me explain. So what we do is we consider D to be the set of all probability distributions on sigma sub k. What we want to find is this particular probability vector. So we want to find this vector, which is p lambda of sigma for sigma in sigma sub k, or I should write that. This is what we aim to find, but we look at D, which is the set of all probability distribution on sigma sub k, and we will try to get this as a fixed point of something, as we shall see. And so D is like, it's a finite dimensional simplex, and we define a distributional map psi from D to itself as follows. So what I do is, to define the map, just pick out any probability vector inside D. So we want to define psi of x vector, okay? So what we do is, we let the root R have Poisson lambda many children. Then to each child of R, I assign an equivalence class from capital sigma k according to the probability distribution x vector, okay? So once you have a realization of this process, you can then, just following this, this argument that you have full information now, you can then determine what the induced equivalence class at the root is of the entire tree. This will be a random induced equivalence class, and this will have a distribution, and this distribution I call psi of x vector. So why do we need psi? Because turns out that this probability vector, which we are interested in evaluating, or not evaluating but understanding better, is a fixed point of this distributional map psi. So here is what our results are, or one set of results are. So we show that psi is a contraction, so no matter where you start from, you are eventually approaching the fixed point, which is what we need to understand. And so the fixed point p vector of lambda is a unique fixed point of psi, and we also show that p vector of lambda is analytic in lambda. Initially, we say that it's just smooth in lambda, and then thanks to Yuval, we corrected that, and we could say that it's analytic in lambda. So that's our first set of results that like heavily involves errand-point games. This is the second set of results that is basically conditioned on survival of the tree. So once again, we are looking at, this is a property that I mentioned, kind of like at the beginning of the talk. Don't have to remember anything. We're just fixing a finite tree T naught, and then we're asking if there is a copy of T naught somewhere inside the tree. And so, conditioned on the survival of the Galton-Watson tree, we can show that this tree is present somewhere. It could be like very deep down, very far from the root, but this tree is present somewhere almost surely. And after that, we can show that if we throw out a bad set of pathological infinite trees that have measure 0 under the Galton-Watson measure, then for any other realization of the infinite Galton-Watson tree, what first order properties of quantifier depth at most k it satisfies is completely determined by a large enough neighborhood of the root. That's combining this result, because all possible finite tree structures appear somewhere deep down inside the root, inside the tree. So all we care about is what happens around the root, and so if you take a large enough neighborhood of the root, that will tell you everything about what first order properties that particular tree satisfies. And this is for almost all infinite trees. And this quantity, so we give a slightly better approximation of this of the radius that we need to consider. It's still of the order of a power, so, or an exponential in k. Omer said that we can do better with 2 to the k. I don't actually know, but we did have a discussion about this. So anyway, yeah. So and then the last thing that I wanted to say is that we also found that the probabilities of these first order properties conditioned in survival, they are nice functions of lambda and p sub lambda, which is the survival probability of the tree itself. And they can be mostly expressed by polynomials and iterated exponentiations. Just a little bit of discussion of the previous.
Can you go back?
Yeah,
The
sure.
probabilities Of which?
The probability of the first order properties, whatever first order property that you're considering. I mean, eventually that will boil down to the first order boil down to probabilities of the radius 3 to the k plus 2 neighborhoods of the root. You know.
So they can't be algebraic functions, just
Yeah.
just compositions, polynomials.
Yeah, I mean, I'm saying that like with kind of a little bit of hand waving, but yeah. So, but they turn out to be like nicely enough expressible, you know. Do you have a question?
But I'm just confused about, is nicely enough accessible really composition of polynomials or also like roots of polynomials? When you wrote before, like for your example, you have a solution of some equation.
Yeah, yeah.
Maybe I missed.
No, go ahead.
So,
So these are the probabilities of the neighborhoods. That's if you fix a neighborhood of the root, then you're looking at, okay, so what's the probability that the root does have this neighborhood?
so this is the probability for an event for all first order or something which is limited to a specific.
So eventually, so these probabilities are of the neighborhoods, and the first order ones will probably be a little more complicated of these, consisting of these.
In the bottom, when you say the probabilities conditions are, this is for any first order property?
No, these are for the neighborhood. Yeah, I should have. Yeah, so sorry about that. Okay, so the conclusion, well, not the conclusion, I guess, though, sort of the future work, or they're no longer future because they're both submitted, one of them got accepted, so yay. This one is the work with Ander, Avi, and Spencer, where I look at existential monadic second order properties of Galton-Watson trees, and I look at similar stuff with Tobias Johnson and Fiona Skerman. This one is submitted, and this one got accepted, so. Yeah, and there are some ongoing works that I don't know we'll see the end of or not, so I didn't mention them, but yeah. Thanks.
Any questions or comments?
I have a sort of philosophical question. This is related to an applied mathematics in the sense like computer science, because I mean, why would anyone study first order?
Right. So the things that we did with Toby and Fiona, they involve tree automata, and these things are used by computer scientists. Like I personally don't know how they get used, but all the references that we could find were like by computer scientists. So, and then Spencer said, I believe Spencer. So yeah.
Maybe I'll make one more comment on that, is that these Galton-Watson investigations are very close to investigating things for just random graphs or the Shreni random graphs. And of course in the background there is a book by Spencer on the strange logic of random graphs. So often questions there, asymptotic questions there, are reduced to these, and these are like the cleaner versions, but maybe for applications one wants to go back and look at.
Yeah, I guess the Erdős Renai is better studied
random
than
graphs.
the Galton-Watson.
And these are captured asymptotically by these.
Okay, so it seems to me that you're suggesting that this can be a method of basically
is
answering questions that could be stated just for random graphs without any reference to logic. But this would be a way to answer them, right? It's a purely mathematical method.
Well, questions that involve logic on random graphs. But the logic, first order logic, does correspond to things that can be handled by simpler programs.
Yeah.
So this is for the sparse setting of random graphs?
Sparse setting.
And what happens in the dense
I
high degree?
I have studied till like C over N. That's the only thing that I actually study. So,
This is relevant to the bounded degree setting.
Does the high degree setting become trivial, or
Yes. Any other questions or comments? maybe I have one more comment. So, wait. I think there is a further thing which Moumanti related to looking at richer properties and also other smoothness properties of the functions. So she described analyticity of first order properties, but actually more general properties or analytic, what's called finite, rapidly determined, things that can be quickly determined if you know the first k nodes with exponential probability of error. So following up on Moumanti's work as co-authors, I've worked on that with Andrew Swan and Perla Susi, but there's a lot more to investigate there when you look at other distributions, other random graph models. So this is very relevant to Erdős-Rényi, but there are lots of other graph models like differential attachment which is studied a lot, and one can ask there are the properties. How smooth are the probabilities of various properties? I think that's okay. But if there are no other questions, let's thank Moumanti again.